We've so far discussed this discrete log problem informally. For the security analyses and claims, it's good to formalize it. So we can do that quite easily using games. And probably the main element that this makes clear that wasn't the case in the informal description is exactly how the inputs provided to the discrete log computation are chosen. And the answer is they're random group elements. So let G be a group. We assume it's cyclic. So we assume little g is a generator. That's what this notation means. Let M be its order. All of these are public. We have an adversary and we have a game called discrete log associated to the group and generator. It's a very simple game. The initialize procedure picks an exponent at random. The exponent is drawn from the space Zm, which means it ranges between 0 and m minus 1. The group element big X is then produced by taking G and raising it to the power little x. This is a group operation. Now, often you might see this game being referred to in an example group like Zn star. If that's the case, this means G to the power x modulo n. We don't write the mod n here. It's understood because we're talking about group operations. This point big X, the group element is returned and the adversary is being challenged to find its discrete log, which is just little x. There are no other exported oracles. The adversary simply trundles along and eventually it says, okay, I think I have the discrete log, and it outputs that. Finalize takes that and just tests if it was correct. Is it equal to x? If so, it returns true and the adversary wins, and otherwise the adversary loses. Naturally, as usual, when an adversary plays this game, there's some probability that it wins. And here we write this to mean the game discrete log with group G and generator G is executed with adversary A and results in finalize returning true. And this is the probability of that event. That's called the advantage of the adversary. The superscript is the name of the metric, discrete log. The subscript says we are measuring security of this group and generator in the discrete log sense. So those are fixed and known over here. So now we can make statements about this advantage or write theorems that talk about the advantage of various adversaries. It would be nice if the discrete log problem were in fact directly the one that we can exploit for public key cryptography. But it turns out that we need a variant of it. And that's the one that underlies the Diffie-Hellman secret key exchange. So let's now talk about that variant. It's called computational Diffie-Hellman. Again, we fix a cyclic group G, and little g is its generator. And it has, we order M. And what is the problem? Well, again, you have as input a group element big X. We know that mathematically it's this G to some power little x, because little x is the unique discrete log of big X. But that's not given as input, and as input you only have the group element. Unlike the discrete log problem, you also have another group element as input, big Y. And of course that's also G to some little y, and you don't know little y. What you're asked to output is not some discrete log, not little x or little y, but the result of taking the generator and raising it to the power little x times little y. Okay, since big X uniquely defines little x and big Y uniquely defines little y, this is a well-defined quantity. And the problem for you is simply find that quantity. Okay, how could you approach that? Well, there's an obvious way to do it. Compute the discrete log of big X. That'll give you back little x. And now take big Y and raise it to the little x. And you see that gives you G to the power Y times X, which is this. So this solves the problem. You could have done it the other way around. You could have computed the discrete log of big Y, got little y, and then raised big X to that power. You don't actually need to compute little x and little y both. You could and then raise G to the power of the product, but You can also do it this way. What this tells us is that if you have the ability to compute discrete logarithms, then you can solve this problem. However, we've just seen that we can ensure that computing discrete logarithms is pretty hard. And based on that, we have a sense that solving this problem is also going to be hard. Now, formally, the assumption that this problem is hard is more than merely assuming the discrete log is hard, because potentially there is a way to solve computational Diffie-Hellman that doesn't involve taking discrete logs. I don't know any such way, and I'm not aware that anyone else does, but it might exist. But since we don't know any, our practical understanding is that the only approach is this one, and thus if we work in groups where the discrete log problem is hard, then we can likely have some belief that the computational Diffie-Hellman problem is also hard. Let's also formalize this one quickly. We can give a game for it. So we again fix our group G and generate a little g, and a little m is the order of the group, and A is an adversary. This game is CDH for computational Diffie-Hellman, parameterized by group and generator. Initialize sets up the challenge for the adversary. The challenge for the adversary is two group elements. How are they chosen? By picking two random exponents and raising the g to the first exponent to get big X and raising g to the second exponent to get big Y. The game stores the exponents, but the adversary only sees the results of these exponentiations. The adversary gets no other oracles, it just has to compute and finally provide g to the power little xy. It provides its guess z to that value, and the game checks that this is correct, and if it's correct, then it says you win, otherwise not. The game note can easily compute g to the power little x little y because it knows the two exponents. The adversary couldn't do that, it had to do something non-trivial to find them. As usual, there's an advantage. It's subscripted by the name of the metric. It's for g and g, and it's the probability that the adversary can get finalized to return true. So this has told us something about the difficulty of the discrete log problem and its companion, this computational Diffie-Hellman, in certain groups. So if you have large prime numbers or we have elliptic curve groups, we now have a sense that we have this problem out there that it seems hard for adversaries to solve. But if we want to actually produce cryptography based on that, it isn't enough to abstractly know that these groups are out there. We actually need to somehow have them in software or hardware. We need to build them, and we need to be able to find all the parameters necessary and then perform computations which allow us to encrypt and decrypt. And so we need to think also about how do we give algorithms to find examples of these groups, and in particular examples where we think that the discrete log and CDH problems are actually hard. So how is this done? We could perhaps first see what goes on in practice. If you look at how people are doing this, you'll see that there are various standards out there which just give you groups. So for example, these are the Oakley primes and elliptic curve groups. So it will simply tell you, here's a prime, and this is the prime, and this is its decimal value, and it's a prime which is about 768 bits long and even been rigorously verified. And then it tells you relative to this prime, there's a generator. So what is the choice of generator here? Type of group, size of the field. Generator is 22. So somehow the number 22 is going to be a generator of this group. And so now that you have those, you're all set. You could have a 1024-bit prime, and then it tells you exactly what it is, and it has the same generator. So And then there are also such constructions for elliptic curve groups. So you could take something like this and then you're all set. You can go start implementing it. This blog has summarized many places you can find these groups. They're called Diffie-Hellman groups. Notice they were responding to the logjam attack, which is the one we saw a little bit earlier here. So for example, Java tells you here's a 512-bit prime. Here's the generator. Here's a 768-bit prime. Here's the generator, and so on. And here actually they duplicate these Oakley things. So that's how it's often set up in practice. Now, how do they get there? Well, sometimes they have ways, and in particular you saw in the Oakley things, that they were actually guaranteed primes. But there isn't, in general, some kind of formula that is guaranteed to produce primes for you. That's something mathematicians have sought, but they haven't quite ever got to. And the typical and generic way to do this is that if you want to find a prime and then find a generator for ZP star, you pick numbers p at random until you can find one that's a prime. And if you pick them and it's not a prime, you just pick another one until you succeed. Once you have the prime, you repeat for finding a generator. You pick elements of the group at random and test until you find one that's a generator. And if you look at what it takes to make this succeed, well, we need to know how to test if numbers are prime. So, because when you pick at random here, you have to test and then see if you need to pick something else at random. Something else, maybe a little more subtle, is that if you're just picking things at random, if there are too few primes out there, your random choices is just not going to find a prime. So we need also to study how many primes are out there. What is the density of primes amongst integers? And the exact analogous two questions for generators. How do you test if a number is a generator once you have a prime? And how many points in the group are actually generators? And you can, once you put this together, you would have some way to create the prime and generator needed to start doing the crypto. Of course, it would be nice if there were something else, some kind of formula or something like that. But in general, those seem to be hard to find. It's interesting to look a little further at this, if nothing else, because it's a place of very productive interplay between math and algorithms, both in terms of techniques and also historically. So let's detail what an algorithm for finding primes would be like under this paradigm. We'll give it as input an integer k representing the desired bit length of the prime. For example, k is 1024, means give me a 1024-bit prime. That means the prime has to be in the range 2 to the power k minus 1 up to 2 to the power k. Now, as per our study of discrete log algorithms, we don't just want any prime. For example, if p minus 1 is a power of 2, it may be that p is very big, but taking discrete logs turns out to be very easy. So we want p minus 1 to have a large prime factor. And the maximal way to get that is to just ensure that p minus 1 is twice a large prime. It can't be a prime because it's even. So the next best thing is twice a prime. If that's the case, the best known discrete log algorithms take kind of the intended time. Okay, so how do we find such a prime? Well, on input k, we pick numbers at random in the desired range, and we test. We halt if p is a prime, but also if p minus 1 over 2 is a prime. And if so, we return p, and otherwise we just go back and pick at random. So this is kind of the detail of what we talked about in the last slide. And but this leads to a couple of questions. How do we do this test? How do we test that p is prime and this is prime? And how long does the loop going to run? How many iterations do we take before we succeed? Because if there are too many iterations, it's not going to be a practical method. So this leads us into all these questions about testing primality and and so forth, where, as I said, we find these nice mathematical intersections. So let's try to test primality. It's a very basic problem. I give you an integer n, and you're simply asked to return true if n is a prime and false otherwise. Well, it doesn't look like a hard problem. How do I do it? I just trial divide. I take various numbers starting from 2 and maybe going all the way up to the square root of n. Why do I stop at the square root of n? Because if there's any non-trivial divisor, there'll be one smaller than that. And I divide n by the candidate divisor. And if a remainder of 0 comes back, I know that the number n is not prime, so I return false. If I get through the list and I don't find a divisor, it is a prime and I return true. So we seem to have a nice way to test primality, but this has the same features and elements as we've seen now often for number theoretic algorithms. It's correct, but it's too slow. The running time is square root of n, which is exponential in the bit length of n. And that's very prohibitive. For example, if you want a 512-bit prime, this is saying this algorithm would take 2 to the power 256 steps to find it, which is absurd. We can't set up a system if it takes that long to set it up. Now, people were very interested in whether it was possible to get a polynomial time algorithm for n. Remember, that would mean its running time is a polynomial in the bit length of n. So in this returns the bit length, something like this. This is a cubic time algorithm. One of the developments in theoretical computer science in the early 20th, well, in the 1960s or so, was the idea that algorithms could be randomized. This means they don't always return the right answer. They return the right answer, however, overwhelmingly often, say except with probability 1 in 2 to the power 100. So for all practical purposes, they're as good as deterministic algorithms. And that slight difference made a big difference to primality testing, and people discovered a cubic time algorithm that was randomized and accomplished primality testing. And this was a very nice algorithm. It takes about a lecture actually to present it. I wouldn't do that here. But it uses elementary algebra and number theory and some elementary ideas about randomized choices. And this was not only important news for primality, but kind of one of the starting points for the whole study of randomized algorithms. It had a big impact on cryptography, which could now use this algorithm for the tasks we've been talking about. Now, theoretically, however, that still left the question open of whether there is a polynomial time deterministic algorithm, and somewhat to people's surprise, one was eventually found. So at this point, we know a deterministic way to test primality in time polynomial in the binary length of the input. The exponent, when it was first done, was fairly high, an 8. It's now gone down maybe to a 6 or something like that. It's still a lot slower than this, so people will use this one. So we can again see these things playing out in various places. You can find primality tests on the internet. So you want to test some number as prime, you can type it in and it should check for you. And it says this is a proven prime. Okay. Why doesn't this solve our problem? Well, you see the little caveat up here. It says I can only test things up to here. There's a maximum, and this maximum is 2 to the power 53. This is a very small number by cryptographic standards. We are talking about numbers which are of the magnitude 2 to the power 512, and that is, astronomically larger than this. So this is effectively pointing out that whatever algorithm they're using is not going to be terribly fast. However, there are faster algorithms. Here's another primality tester. We can run it on various numbers and it'll check. Maybe it'll tell us something about what kind of test it's using. And we see the code for the test here. What does it do? It checks whether a few obvious things hold. Is it even or divisible by 3? And otherwise it actually just tests divisibility, kind of like our naive algorithm. So these online things are not implementing the fast algorithms. Here's another curiosity. People try to figure out what's the largest prime that anyone can actually give, and this has to be proven to be prime, not that there's some probability it is or something like that. And this is how far they've got. So this is a ginormous number, right? It's way bigger even the numbers we're interested in. But uh, it took some amount of computation to find it like this. You can also find on the internet lists of primes. Maybe if you're looking for a prime number, you could say, okay, I just go to this list and they'll simply give it to me. So um, you can, and I think it'll show you, you can keep going farther and it'll find more and more numbers in the list. But it tells you here, this is a list of prime numbers up to 1,000 billion, right? So they haven't done the computations beyond that. Could you find something of crypto value in here? Well, let's ask, how big is 1,000 billion? So 1,000 billion is actually a trillion, which is 10 to the power 12. So what we're asking, or I want to ask is, what is the bit length of 10 to the power 12? How do I get that? Well, the bit length means 10 to the power 12 is 2 to what power? How do I get that? It's take the log base 2 of 10 and multiply by 12. And the answer is about 40. So this says that this list of primes is only going up to about 2 to the power 40. And remember, for cryptographic purposes, that's way too small. So we want primes of about magnitude about 2 to the power 500 or 2 to the power 1000. This one speaks a little bit to this problem about finding not primes in this case, but generators once you have a prime. And what it says is that there's someone here is posing the question, is there an explicit formula that will find a generator of a cyclic group given a prime P? That's exactly the problem we would want to solve once we have a prime. And you can see various answers here. It says strictly it's still a conjecture. Then this person says, for any non-identity element in the group, we know that a to the power p minus 1 is 1 mod p. Yes, we do. And in fact, we know that in this class as well. Why is it true? Because p minus 1 is the order of the group zp star. And we had a theorem saying anything to the power of the order of the group is the identity element. But this person now concludes that all elements except one are thus generators. But there's no particular reason to conclude that, right? So in fact, that conclusion is incorrect. And then the person recognizes that. Not right, as p minus 1 may not be its order. Not sure what that means, but in any case, there's another answer over here. This one tells you something that's also interesting for us to know, which is you can count the number of possible generators. So a cyclic group of order n has phi of n generators, where phi of n is the Euler function. So phi of p minus 1 if you're looking at zp star, and remember that's the size of the group zn star. Okay, but that doesn't actually necessarily give you a formula for them, and that later discussion figures out. So it's kind of interesting to see people talking about all this stuff. Anyway, coming back to our story, we have ways to do primality testing. But we were trying to find primes by this process, and we had a second question. How many iterations does this algorithm need to succeed? Well, it's going to succeed whenever a random number chosen here as a prime. So effectively asking, if I pick things at random, how likely are they to be prime? So let's let pi of n be the number of primes in the range 1 through n. So if I pick a number at random from 1 through n, the probability it's prime is now given by pi of n divided by n, obviously. So if I know something about pi of n, I can determine something about this probability, and thus something about how long the algorithm will take. It turns out mathematicians have studied pi of n for a long time, and they know that it grows roughly like n divided by log n. And this is actually saying that there's quite a lot of primes out there. So now if you plug it into the probability statement, the probability that p is a prime turns out to be 1 over log n. So even if n is like 2 to the power 1024, this probability is like 1 in 1,000. So it says our algorithm takes about 1,000 executions to find a prime, which is fine. And that tells us that it actually is pretty practical. This is another nice intersection of classical number theory with algorithms and cryptography. So we started out this whole quest of number theory by looking at the Diffie-Hellman key exchange. And this simply shows you the exact same protocol I had written way back at the start of this chapter. And my claim is now, if we relook at it, things will make a lot more sense. And we will know not only what they mean, but how we might implement them. So remember, the protocol says that a prime P is public and a generator G of ZP star is public. Alice picks a random exponent, little x, in the range zp minus 1, yp minus 1, because that's the order of the group, zp star, and then raises g to the power little x, mod p, to get back big X, sends big X over. Bob likewise with y, sends big Y over. Now, if you take this big Y and raise it to the little x, or if you take big X and raise it to the little y, you get back the same thing, which is this, and that becomes the shared key. On the other hand, the adversary trying to compute this key is faced with the problem that we now recognize. It's the computational Diffie-Hellman problem we define. We had asked all these questions. How do you pick a large prime and how large is enough? We now have answers. We can use the algorithms we just saw to pick a prime. You pick numbers at random and you test them until you find a prime. So you would use our primality testing algorithms. You would use the formulas we saw earlier to determine how long the algorithm ran. How large is large enough? Well, you need the discrete log problem to be hard. Well, we estimated that. We gave information about even experimental results telling us just about where people have reached in discrete log computations. So a good answer, for example, might be, 1,000 bits at least would be good. We said that G was a generator in that protocol. What does it mean to be a generator mod P? Well, we now know what the definition is G is a generator of the group ZP star. That means the powers of G yield all possible group elements. How do we find a generator? Well, we talked about that. We didn't give a solution, but we mentioned that one exists, and we saw a little bit of internet discussion. How can Alice and Bob quickly compute what they need? Well, they need to raise G to powers. It's not, if you do it naively, it would be way too slow. But we had our modular exponentiation algorithm, which did it in cubic time in the lengths of the inputs of the numbers. So now we can do it pretty fast. Why is it hard to compute the key? Why is it hard for the adversary to compute the key? Well, if you look at what it sees in the protocol, it sees what Alice and Bob send, which is big X and big Y. And that means that what its job is to solve the computational Diffie-Hellman problem. And we've decided that that was not that easy to do. So that